Good morning, everybody. This is Kevin Bai, Associate Professor in University of Tennessee. Today, I'm going to report the project sponsored by Power America to package a 650 volts high current gallium nitride module. This module will not only include the thermal solution, but also include the gate driver, basically integrate the gate driver in. The key team member of this project include General Motor, Hala, GaN System, and the University of Tennessee. So why do we need this project? First, if you look at the GaN devices on the market, majority of the GaN is about 60 ampere or about 80 ampere for the discrete switches. Now, if you want to use a high current, you really have to parallel many switches, parallel the discrete switches. That's not going to facilitate the usage. No mention you have to put the gate driver outside, which will need you to route all the traces, thereby increasing the parasitics and slowing down the switching speed. Now, the other thing is a lot of the discrete switches have their thermal pad non-insulated. In other words, if you want to attach it to the heatsink, you really have to place a thin layer of thermal material in between, which will somehow worsen the thermal performance of the device. So the mission of this project is to first see if we can integrate the gate driver in, thereby making the switching speed, maximize the switching speed. Secondly, is to see if I can somehow eliminate the unnecessary thermal materials by using the direct bond copper. In other words, we solder the die directly on top of the copper, then the DBC, then attach the DBC directly to the heatsink. Okay, so we can find the immediate use for such a device, such a power module, especially in onboard charger and the motor drive inverter. And also the graduate students are involved in this project to leverage the ongoing DOE wide bandgap traineeship program in University of Tennessee. Now, expected outcome of this impact include, first, of course, we will provide the integrated gallium nitride module. Secondly, this module will have pretty decent thermal conductivity. Thirdly, it will, of course, with such module, we find you can use it in electric vehicle, thereby expediting the GaN applications in EV industry. Fourthly, we engage our industry members. GaN System provides the die, Hala and GM provides the design guidance. And in this process, we involved 3 UTK graduate students and 2 IU students, one of which is a domestic master student sponsored by DOE wide bandgap traineeship. At the end, we hope the outcome of this project will yield new courses. Yeah, will yield a new course to be offered in spring 2020 in 2021 in University of Tennessee. Now, to give you the overall what this module really look like, first, you see on the right corner, we have the overall layout of this module. We have a bus bar, we have the PCB integrating all the decoupling cap, gate driver, power supply. The switch is sitting in the middle, then the switch is soldered on top of the DBC. Okay, the overall dimension is about 45 by 34 by 9 millimeter. Okay, it's quite a compact module. Okay, eventually we will package all of this module, and I would say for now we are already packaged probably 80% of this module, except some of the bus bar to be soldered. Of course, we promised the pretty good thermal performance. Therefore, designing the DBC will be one of the key points. If we look at the overall breakdown of the devices, we have the die, top copper, ceramic, which is aluminum nitride. Then another copper sit on the heatsink. Okay, so overall, our preliminary simulation shows the thermal impedance of each die is about 0.33 Celsius per watt. So what does this mean? This is very similar to the silicon-based power module already. Okay, no mention our device, the module we packaged here is super compact. Now, the second step will be designing the smart PCB layout. As I said, this PCB will integrate nearly all the dies, will integrate the dies, the power supply, the gate drivers, and eventually all you need to do is to provide 0 to 3.3 volts PWM signal. Then the rest of the work, meaning how to convert the PWM to the gate signal, will be taken care of by this board. Okay, and to save the cost, after consulting with GM and Hella, we decided just to use a 4-layer 1-ounce copper to save the cost. So there's no exotic PCB design. Because the special thing is for this module, all the current is traveling from top to bottom. There's no current traveling in between. In other words, no current traveling horizontally. Therefore, we really don't need heavy copper. Now, of course, when we lay out the PCB, we hope we can minimize the leakage in the street inductance. Therefore, we managed to put the let's say decoupling cap on top and the 2 GaN devices on the bottom. So at the end, you see that we can form a flux canceling loop. Our analysis shows the loop inductance for one device, for one die. I would say one die from the bridge will be like 1.54 nanohenry. Now, if we are talking about 2 dies, then overall that will be 0.77 nanohenry. Okay. Now, whether this one is good or not, let's use the experiment eventually to validate it. At the end, we we have the DBC, we have the PCB, so it's a time for us to solder the PCB, then solder the die, then solder the die directly on top of the DBC. So we have totally 3 layers. Okay. On the left side, you see we already have this module nearly, I would say probably more than 80% ready. The rest of the work is just to solder I would say solder the bus bar on top of it. We can translate 0 to 3 volts pulse, PWM pulses into the -5 to +7 gate signal. That's good enough for the present GaN devices. Okay. Then at the end, we also did a test. We promised in SOPO to design the maximum current voltage to switch is 450 volts. That's probably the highest current battery voltage we are going to face in the reality, and also much larger than 150 ampere. So this DBC, this double pulse test really shows we can switch on off these devices at 450 volts, 150 ampere without any issue. And if we look at the switching performance, we probably more care about the voltage spike. Now, if we look at this voltage spike, originally we thought we are going to have less than 100 volts. Actually, in the real design and the real test, we find it's even better. We find the voltage spike is quite small. It's about only 54 volts. So we call such design is a success. The rest of the work, as I said, will be first, we need to test the thermal. To validate the thermal will be really as good as we claimed. Then lastly, we also would like to put the bus bar in, then eventually really form a module for the applications. Okay, with that, I'm going to wrap up my presentation. And if you have any questions, you see my contact here. Feel free to contact me. Thank you very much.